Hey everyone, today we'll be going over how I made artificial intelligence to see blood, and without any further hesitation, let's get started. Hey everyone, so I'm here to talk about my first master thesis, XMARCUS I, where I built a computer vision models to actually 7 components of anatomy, really focusing on classifying and seeing blood actually in the midst of cauterization of smoke. So I'm here to just showcase a Medium article just summarizing my whole master thesis, and also showcase the presentation slides for it at the same time. So yeah, just without any further hesitation, let's dive in. So the premise of this entire thesis was to be able to explore a different paradigm and application within computer vision, because there was a lot of work that was already taking place between surgical conferences that I was doing since I was an undergrad, and publishing the Journal of Surgical Endoscopy. Really, they were starting off with literature reviews, but then there was a big push in terms of software development and advanced software to classify components of anatomy in real time. And throughout the scope of the thesis defense and the write-up for the manuscript, I make an application for utilizing machine learning to classify components of anatomy in real time. But I wasn't the only one who was coming up with this idea. There were cohorts of surgeons and ones who were on the boards of the triple AMC. And they were actually writing books about artificial intelligence applied within surgery. And so throughout this whole thesis defense, what I did is that I broke it down into 3 sections. I first give a hardware overview in general, first talking about exactly like, hey, this is what I contributed over here. And I broke it down into 3 parts. First part, I give a hardware overview for robotic surgery. Second part, I focus on applications within robotic surgery for advanced software. And then I also showcase a data set that is on Kaggle, given the amount of images I had to do is roughly about 13,000 for annotated images for a diaphragm dissection, where I was able to actually, well, this is the CVAT annotated image, for instance, where I was differentiating between the endoscopic risks and the amount of blood as well. Then I also talk about the third part for policies, as well as like a discussion piece over there as well. Since I was, for my undergrad and first master's, I was at Virginia Tech, and Virginia Tech has a big human-computer interaction hub over there. So with that, that was why in particular there was this third part for the applications of artificial intelligence inside of robotic surgery. And so I'm just going to give an overview in this video talking about the Medium article and my thesis defense, and I have all the slides already up here just in this article, so you can feel free to browse and take a look at it. So I'm just going to give a quick overview about what it was that I did and what I defended to be able to get my first master's degree. So yeah. Overall, so I just start off with the presentation over here, and first off I just gave the introduction about doing typically for a master thesis defense, you would have to give a literature review to be able to start reviewing the rest of the literature that was already set up in place. And these pictures I took while I was at the conference at the same time, or series of conferences as well. And then what I had to do, and this was just an overview to begin what was already set in place for the thesis. And initially I start giving an overview of robotic surgery. I talk about the history between different pieces of hardware that were utilized, really. There's an interesting component within robotic surgery, really, between just how it was adapted from manufacturing robots to then be applied within within the surgical room as well. There was a Puma 560 as well that was a big breakthrough, and and it wasn't until that Frederick Moll of Intuitive Surgical, who founded the whole company, managed to acquire the license from the patents that were made by NASA to be able to start Intuitive Surgical, which is what I had to make for my defense on the history of it. Then I also talk about a theory called the diffusion of innovation, made by some American sociologists. I was talking about really just about different groups of people who are willing to adapt and sort of accept new forms of technology and different means of practices, because surgery really is a very, has its own nomenclature of people that already have their own modes of doctrine and residency that were already going for their practices and such. So if you are trying to introduce something new in the medical field, there's a lot of regulation and administrative legwork that needs to be done to be able to implement one for surgical practices, as well as credentialing at the same time, whether hardware or software at the same time. And throughout the rest of the master thesis, I also give an overview for the hardware of the equipment for the most part, and where I was trying to focus on software. Really, I was focusing on the endoscopic camera for creating models to be able to see different components of anatomy. So it was really this endoscopic 3D HD camera that would typically be used inside of in vivo surgery. So throughout the overview of the hardware for the present definition of robotic surgery, I first had to give like an overview based on the field and exactly like how it started off for the defense. And then the next part of the master thesis, I had to focus on application. Here I talk about, and these were different layers of images that I had throughout the rest of the presentation, hence why you see them stacked. But really I was talking about over the aspect of computer vision applications in the medical field, because there was a big advocacy for, as you can see in the presentation when I was over there in Vegas, for what they were talking about. They were already trying to do overlays of images, and they would already have these physical mediums that they would already be set up in place, like having green dyes to be able to actually see, and different components of anatomy in real time to differentiate what one was looking at as like an image-guided intervention type of methodology, and different practices as well. People would use physical indicators, whether wires or dyes, but for software, on the other part, this was a big part that a bunch of surgeons are currently still looking for their critical applications, as different groups of them are writing multiple series of publications and releasing books talking about it right now, hence the R&D research phase of what was going on. So that was a viable thesis for me to be able to actually tell to professors at schools when I was getting my advisory committee to be able to make the defense. Really was like, hey, computer vision applications, this is what surgeons are looking for. And so as a result from that, I decided to like take back from what I learned from the conferences and be able to make a master thesis of it. And this was just another example. Augmented reality over here. And yeah, this slide was just also just to give in representation. MICA is a prominent conference really that focuses a lot in robotic surgical vision. They have challenges at the same time, and then creating new artificial intelligent models to classify components of surgical tools widely, and instant segmentation at the same time. There's been a lot of work to talk about segment components of surgical tools, but in this slide, what they wanted to go for, one, they can talk about like, hey, we're able to see from the naked eye and classify different tools, but to be able to get to the next step of anatomy, now that stuff has not been done before in terms of, hey, we want to be able to see the anatomy in real time, get the information about it, and allow us to break through each of the following steps so that way we can have an over-encompassing view to go through step 1, 2, 3, and 4 in that context, but also there are different psychomotor skills that also need to be taken place for surgical skills. But having the present information right there, right in front of us, to be able to see exactly from an over-encompassing view, and typically there would be a series of overlays that would happen, and this is also like a mix between augmented reality and then machine learning as well for classification, but they want to be able to see the present information already right there, so that way they know exactly their entire environment. However, a big problem that is with the current idea is that based on the fundamental practices between artificial intelligence from its present definition and computer vision, the applications within surgical anatomy are very young and very novel to start with. However, there's been a strong history of computer vision from people with the NASA Jet Propulsion Laboratory, where they're able to apply it in for flights and simulations and such. However, putting it into this domain is a challenge in itself that's really quite promising for the most part. So that was my first master's thesis just going over. And a big problem that is really coming into the medical community that is kind of a hurdle and challenge, because they want the idea of applying this form of technology, but there's a lot of data regulation that goes into place because of HIPAA compliance and FDA high-tech policies at the same time, because it's just patients' data whenever they have the recorded information, whether what's inside of them to be able to start with. But they're trying to figure out how to make data compliance a big policy type of issue that will be complacent with both patients as a party, hospital and hospital administrators, then the surgical community, academics, and then engineers, trying to bring them all together in that case. And I had to make another point during the master thesis on that whole thing. And then I also give a list about problems, really. Really a connection between the AI winters, and then also understanding between scalability and distribution in terms of artificial intelligence applications in the field of robotic surgery and within in the medical field, because I was focusing on robotic surgical vision for this thesis defense, and also like how do we annotate said data, how do we get a hold of it, what do we do to be able to create artificial intelligent models that can classify components of anatomy, I had to make that giant application for this defense to be able to be awarded my degree. And what are the implications whenever we have to train surgeons utilizing this advanced form of software as another means for education to be able to help them with surgical skills and psychomotor skills as well, and present knowledge and information that's already right there. So I had to come up with research questions. These were the 4 that I had to tackle in order to actually get my defense already viable, like saying, hey, this is something that is independent thought, that is already right there, so I can be awarded the degree. And that way you can ride off in the sunset with what you can do with it and advocate saying, hey, I did this intense research project and, I got a manuscript and a publication and people can talk about it and stuff. So I talk about these 4 questions that I have over here, and then I just go over into the next phase of exactly like, hey, these are the approaches that I decided to take over here. Create a public annotated data set, walk through approach for crowdsource annotation, and I presented an overview of FDA regulations and avenues for third-party development for novel applications, and then also talk about the future frameworks for surgical simulation to implement novel AI practices and connect further domains to prevent another AI winter in surgery, potentially, because there was a AI winter in the 70s that's quite talked about and prominent. Because of the definition and the funding and the direction that was going in, because in 1956 there was the coined term of artificial intelligence, but it wasn't until that there was some activity going on, but then it wasn't until a couple experts started questioning about it, and there was a book that was released called The Perceptron, and then another person on a really high research committee advocated like the present definition of artificial intelligence doesn't have any like applications and so forth, and so there was an AI winter that was going on, which means that there was not that much research activity going on during that period. And that was a question that they were already talking about in terms of mitigating against AI winter, but I bring it up for the defense at the same time. So then there's this book by Dan Hashimoto. We happened to meet, actually. I was very fortunate enough that we happened to meet when I was an undergrad, and I was the only undergrad at the surgical conference there. It was at the World Congress of Endoscopic Surgery in 2018. And I was fortunate enough to be able to meet Dan and everything else, and he happened to release his book, and I thought, well, that's pretty cool. And he was doing some stuff at MIT Sale, and right now he's at UPenn, but yeah, there was a book that was released about it from the surgical community, engineering community, and groups of people come together to talk about artificial intelligence in surgery. There's already a book called Artificial Intelligence in Medicine by Houghton Ashrafian, who is my academic advisor from Imperial. He wrote that book along with a cohort of his colleagues and friends as well for it. So there's a lot of work that's already going in talking about artificial intelligence within surgery. It's just niche because it's research. It's really in-depth type of research field for the most part for biomedical engineering applications. So yeah, this book one can buy on Amazon right now for it, and it's published through McGraw-Hill. So the next part of my thesis defense, I talk about a created data set actually that I made that's available on Kaggle, and I'll put the link in the description as well. So the first part that I had to do in terms of the data set is one big thing that always comes in with artificial intelligence development, whether machine learning or deep learning, depending on the complexity of the nodes, is one, your data. Like, how well are you going to annotate it? What's the use case for it? Because really, the steps you need to develop is that one, you need lots of data. Second of all, you have to use a proper model architecture, and then with the model architecture, be able to train your said model with the provided hardware resources as well, to be able to actually say, hey, I have a model that's able to pick up the number of patterns for, depending on exactly what context you want to put in, whether for computer vision or natural language processing, for said application. And the application, the problem was already stated right here. In engineering, we have to come up with, we have to take everything from the abstract and make something that is practical. That's what I like about it. And this was just an example that I had to give. I had to figure out in terms of how to annotate the data for the most part. And I was very fortunate enough that Dr. Avid Lin, one of my advisors who was in the computer vision department, well, his field talks about computer vision. He was in the computer engineering department at Virginia Tech, and during that time, he actually introduced me to CVAT, which is Intel's computer vision annotation tool, and I used that to be able to create this data set, which allowed me to be able to create a comprehensive JSON file to be able to train machine learning models, where I did a comparison study against 5 of them that were non-pre-trained. I'm going to talk more about it later. So, excuse me. Luckily, even though there's a lot of regulation that goes in with data compliance in terms of releasing it to open source and the direction about where where it's distributed. Imperial College London, where that's also my alma mater as well, where I got my second master's, happened to release an endoscopic video data set of raw stereo images. Now, mind you, I state raw because in of itself they're non-annotated to be able to start with, and they have robotic-assisted surgery videos and endoscopic video and laparoscopy at the same time. So that way people can play around in terms of with the video data set, use it for computer vision applications, and yeah, it's pretty good to be able to start with if one wants to be able to just dive further in depth in computer vision, its applications and stuff. And I made a workflow to be able to actually utilize a very niche tech stack called Intel's OpenVINO framework. So OpenVINO is a phenomenal computer vision tech stack if you want to get started in terms of creating your own artificial intelligence models for computer vision, because there's a lot of expensive open model zoos that Intel released for the deep learning workbench. I'm going to get to it soon, but it's inside of the OpenVINO umbrella, and it allows one to be able to actually see everything from a visual standpoint for the model that one is able to actually have. And so this was a workflow that I actually had to use. So there were, in the book AI in Surgery that I showed a while back, they were talking about crowdsourced annotation as a concept of loads of people come together and annotating said data to be able to actually make classifications in terms of this is surgical anatomy, this is an endoscopic tool, this is healthy tissue, non-healthy tissue. And it's a very encompassing type of problem for the most part, based on the present definition of computer vision and artificial intelligence and what we know in terms of its philosophical approach to its application. I don't mean to say philosophical approach, but it really does come down to the mathematical logic that really came in to develop the perceptron, as well as like neural networks and how to develop artificial intelligent models based off those neural networks, depending on exactly the complexities and architectures and the applications of them. So I tested 5 different convolutional neural networks as a comparison study that had instant segmentation masks and had different number of parameters, but I'll get to it. But anyway, this is the workflow that I had to be able to state, hey, if we got a user, they first got to get data, they got to annotate the data, then they got to export the following annotated data in different frameworks that would actually be fitted. You use Coco, Onyx, or PyTorch, or TensorFlow, depending on exactly what libraries one is actually able to use. I think I used Coco for this, and then I called upon a deep learning workbench using Docker, so I can test out myself locally and be able to utilize my GPU and Intel frameworks that I was also using at the time, because I had my own laptop that I was actually running this on with a 2080 GPU during that time period, because it was just easier for me to train stuff locally. And plus you will get faster development that way and quicker iterations, especially when you're creating models from scratch. But that's for like my next thesis, because I developed 3 different models that I'm making a comparison study on. I also misspelled selection, I apologize on that. And then we would select the environment, select the validation set, import data image, and create the project. So this was the video right over here for the CVAT annotation that we have. So this is exactly just one example that I would just have in terms of like, hey, this is an segmentation mask. But a big problem that I actually had to, there's a lot of research that really goes in terms of like, hey, we have this application that's right here. It's able to see different parts of it, but this is just really creating the very in-depth JSON file that we would use to be able to actually make different forms of classification that would come out already set up in place. Then I give an introduction about the Intel's OpenVINO framework, what it is, what it talks about, and then I also talk about their deep learning workbench, where you can utilize it via Docker, and I have a link in this as well for the for anyone to be able to take a look at it. You are going to have to download this. I used Anaconda and Windows PowerShell to be able to actually like download on this. So depending on your platform and depending on what you're using, you work with Deep Learning Workbench. If you get this signal, that means, hey, it's fully downloaded and it's good. Helps as well when you get Docker and be able to run the various containers that you have to be able to run it locally, and then be able to interface with whatever model that you have. And in this first master thesis, I tested 5 different instance segmentation models that are not pre-trained, because one, with a lot of open model zoos that are typically on the shelf, a lot of them are typically pre-trained with open source data sets that have a lot of images, like ImageNet, where you're able to take a picture with your phone, for instance, out in the public and out in the air, and you can have models that can classify cars, you can have them classify trees, you can classify people. But if you're going to be doing something so niche and so specific like endoscopic anatomy, there's not that much, one, because of the issue with the data that is already available, or lack of, you're not going to have that many data sets that are going to have that are going to be already pre-trained with set models as well. So I defined non-pre-trained models in their OpenZoo library and make a comparison study based on their accuracy and such. And throughout that whole scope, I used instance imitation non-pre-trained models that were convolutional neural networks as well. I will pull up the architecture and put it inside of the description as well for them. So I had 4 different labels to be able to begin with for the classification. It was blood, trocars, and I think it was healthy tissue, and I forgot the other one. I apologize immensely on that. So I did a comparison study between 5 different non-pre-trained models, and I actually, they have Intel's OpenVINO framework has a phenomenal interface to be able to actually, one, load your data set in, and then have the model actually be trained locally, and already have their already have everything already set up where you can configure and where batch processing is already taken care of depending on exactly the number of images. Make sure you can split between 80 20 and 10 or 70 20 no, sorry, 80 10 10 and then 70 20 10, depending on exactly your preference in that, so that way the model can actually have a viable output. And so this is already available on GitHub for the instance imitation models. You guys can take a look at it. The articles in the description, and also a comment as well. And I also have actually 6 of these, not actually 1, 2, 3. But regardless, I've just made multiple copies of this, so I'll just clean it up for you folks and then be able to output it out. So then I actually put this slide in the presentation because when I was doing the testing of this, I was incredibly proud of this result. Like having my own machine learning model be able to see blood for the most part in the midst of cauterization of smoke, because of the raw video that I would initially have. A big issue that I was facing was, one, this is a stereo image. This is not high fidelity to be able to start with. Second, the other problem was actually seeing instances of bleeding during cauterization of smoke, especially in endoscopic viewpoints, because you have a limited view, because one, you don't have level of depth. Second, if anything were to go down in particular, the most common forms of problems for robotic surgery are typically broken pieces falling into patients or electrical arcings happening. If you have something that's obstructing your vision while there's something going on, you don't know exactly what's going to happen, and that can actually lead to further hospital stays, longer stays, and then there can also be patient litigation against a hospital at the same time. So having instances of bleeding during cauterization of smoke for the model to be able to predict was such a huge achievement, and it was like very euphoric to be able to start with this, because it's like, hey, you know what, this problem is actually already right here. This is something that's actually coming together, and for it to actually make that prediction was just super sweet in that case. And then I did a comparison study of the accuracy based on Intel's OpenVINO environment, because they have a comparison where if you actually have your validation data set, you can actually take individual images and then be able to actually see the comparisons between how well that it's able to accurately predict, like, hey, is this blood? Is this healthy tissue? Is this, are these trocars in particular, because the models can actually pick up the trocars pretty well, but when it came to blood and bleeding, which was what the surgeons were actually focusing on, that's another challenge to be able to go through in that case. And also, you're subject to the quality of the data, the amount of data that you have, how well the models, in terms of the number of parameters, and the given preference of model architecture as well. These were instance imitation models of convolutional neural networks that used, I believe, the ReLU activation function, and then used sigmoid as well. And I think the atom optimizer at the same time. But yeah, I did a comparison in terms of accuracy based on Intel OpenVINO's platform for what they had. And then after I got the results and everything else, I talked about the discussion and the ethics between artificial intelligence, applying machine learning models for clinical application. How do we reduce a patient length of stay? Because from what I got from the surgical conferences, that one metric that hospital administrators love is reducing the patient's length of stay. And using new forms of technology and such. And I talk about the feasibility of applying such technology in practical scenarios and clinical applications, and then the ethics of employing machine learning modeling to enhance surgical performance and recognizing components of anatomy without using injectable dyes, for instance, or physical indicators, using advanced software to be able to actually see the different levels of anatomy in real time. Then I talk about the policy aspect, the training surgical gap. How do we reduce this? Because there's typically residents that have already come in, especially when they're learning about new surgical techniques at the same time. They got to get used to psychomotor skills. There's further credentialing at the same time for the practices as well. Because according to the author of the Emperor of Malatus and the Gene and Intermittent History, he stated that surgeons are, in his words, are like small business operators for the most part because of the skills and knowledge and Rolodex that they were already released. This is exactly the practice that they would have. Then I talk about FDA policy and regulation, and just based on the regulation for what I did for a literature review based on the FDA was that I was focusing on exactly like, hey, education's a field that can actually be used in terms of implementing new and novel forms of technology because of lack of regulation. That's already right there, but I wouldn't say lack of regulation in that term. I would say they have more generous terms in terms of putting in for education rather than putting in a real-time surgical framework. That's why, in particular, for instance, if you have anything like robotic surgery, gastrointestinal and urology are widely used portions of where robotic surgery and its applications are used. And there are neurosurgeons, for instance, in London that are practicing, that are using robotic surgery either in gastrointestinal or urology to be able to actually get further used to it for robotic surgery, because there's not that many novel robotic surgical consoles for neurosurgery, for instance, because you have experts in the field that say, oh yeah, the robot's too big in particular, but you still have surgeons gravitate towards this because of like, it's robotic surgery, it's cool, you know, it's another form of surgery that's able to reduce a patient length of stay, and then be able to actually help in terms of like reducing patient length of stay through minimally invasive surgery. And then I also talk about cloud robotics at the same time in terms of getting information already out there. If we have a model that's already in the cloud, for instance, how can people be able to interface it throughout every single different form of hospital, much like in the case of ChatGPT and how it's released on Microsoft Azure backend. In that case, and everyone's interfacing with it. Then I also talk about Ken Goldberg in terms of his work with cloud robotics as well, and the Robot Garden at the same time. So it was just something that when I was meeting Ayanna Howard, she introduced me to his work, and I obviously just like, oh, this is really cool and interesting. I didn't talk about the case for remote curricula because it was just advocated in terms of human-computer interaction from where I was in my environment. And I talk about third-party development at the same time. How do we make the whole interface on it? So this third part was for the discussion part. Then talk about the conclusion for the whole thesis, and then talk about the future work for artificial intelligence in translational medicine. And that was the end of my thesis. So yeah, this was my work in terms of my first master thesis to be able to get my degree of how I was able to create artificial intelligence to be able to see blood. As a result from it, I got awarded a first master's degree. That's basically what happened throughout the whole thing. And yeah, I'm going to have this article already up for everyone to be able to see, play around with it, and then yeah, just interface with it. Feel free to take a look at it. Feel free to go through the steps in terms of actually like going around with the tech stacks that I mentioned. And yeah, thank you all very much for taking time to watch this. If you found this video helpful, be sure to feel free to please like and subscribe. Or if you found this video insightful and you enjoyed further information that you have learned throughout this video, feel free to please like and subscribe as well. And if you have any questions in regards to just what was mentioned, please put it in the comment section. I'll be happy to answer them. And yes, best of luck to you in your endeavors and all. Cheers. Bye-bye.